The James Webb Space Telescope was built to look deeper into the universe than anything humanity had ever launched before. A golden eye floating nearly 1,000,000 miles from Earth, parked in the darkness at the L2 point, far beyond the noise of our planet, staring into light that began its journey before Earth even existed. But some of the things Webb has seen do not feel like ordinary discoveries. They feel like warnings. A distant galaxy, shining too clearly from the childhood of the universe. A star system, where planets may hold the ingredients for life. A dead star surrounded by something that should not have survived. Moons in the outer solar system, showing heat where there should be none. A galaxy pulsing in infrared with a rhythm too structured to ignore. And a mysterious star dimming as if something massive, flat, and artificial were passing in front of it. For decades, we believed the universe was silent, cold, and indifferent. But Webb is forcing us to ask a darker question. What if the universe was never empty? What if the farther we look, the more we realize that space is filled with patterns we do not yet understand? And what if some of those patterns are not natural at all? When James Webb began scanning the cosmos, astronomers expected surprises. That was the whole point. Webb was designed to see in infrared, to pierce through cosmic dust, to look deeper into ancient light, and to reveal objects too faint or too distant for previous telescopes. But what Webb began to reveal was not just more detail. It revealed tension, patterns that did not fit comfortably inside the models we thought were stable. One of the strangest examples came from much closer to home than distant galaxies, Neptune. This cold blue planet, orbiting in the outer shadows of the solar system, had long seemed quiet and remote. But new observations showed that Neptune's upper atmosphere had cooled dramatically over a relatively short cosmic time scale, nearly 10 degrees Celsius over just a few decades. That may not sound like much on Earth, but for a giant planet at the edge of the solar system, it was alarming. Solar activity did not seem strong enough to explain it. Internal heat variations did not provide a simple answer. And then came something even stranger. Subtle changes in Neptune's magnetic environment. Faint rhythmic disturbances that looked less like random noise and more like a pulse. Was Neptune simply reacting to natural processes we do not yet understand? Was something unseen influencing its atmosphere and magnetic field? Or was this the first hint that the outer solar system is more dynamic than we ever imagined? That same unsettling theme appeared again when Webb looked toward the moons of Uranus and Neptune. These small frozen worlds were supposed to be dead. Ancient icy remnants orbiting too far from the sun to have much activity left. But infrared mapping suggested unexpected thermal signatures on moons such as Hippocamp and Despina. Heat in places where heat should have faded long ago. On their surfaces, Webb detected complex carbon compounds, possible organic precursors. The kind of chemistry that makes scientists stop and look twice. How can small icy moons orbiting in the deep cold maintain internal energy for billions of years? Radioactive decay and tidal heating may explain part of it, but the deeper question remains. How many worlds have we dismissed as dead simply because we never had the right eyes to see them? Webb is showing us that the solar system itself is not a finished story. It is still hiding heat, still hiding chemistry, still hiding motion in places we once called frozen and lifeless. And if that is true here in our own neighborhood, then what is waiting in distant galaxies? Then Webb turned its gaze toward one of the most famous planetary systems ever discovered, TRAPPIST-1. Just 39 light-years away, this system contains 7 rocky planets orbiting a small red dwarf star. For years, astronomers have been fascinated by it because several of those planets sit in the habitable zone, the region where temperatures might allow liquid water to exist under the right atmospheric conditions. But before Webb, much of that hope was theoretical. We knew the planets were there. We knew their sizes and orbits, but their atmospheres remained mysterious. Then Webb began studying them in infrared. By analyzing starlight passing through planetary atmospheres, Webb looked for the fingerprints of molecules, tiny absorption patterns that reveal what gases may exist around distant worlds. And what it found was extraordinary. Signs of water vapor in the atmospheres of TRAPPIST-1d and TRAPPIST-1e. Not just a faint hint, but indications of atmospheres that could be humid, dense, and chemically active. Then came the even more provocative detail. Ozone-like compounds, molecules that on Earth are associated with atmospheric chemistry connected to biological processes. This is not proof of life. That distinction matters. But it is something almost as powerful. It is proof that the search is no longer abstract. For centuries, humanity wondered whether other worlds could be alive. Now, for the first time, we are beginning to read the chemistry of rocky planets around other stars. And TRAPPIST-1 may not offer one possible world. It may offer more than one. Imagine that. 2 rocky planets in the same system, both carrying atmospheric signs that make scientists wonder whether biology could be possible. Suddenly, the question changes. It is no longer only, can life exist elsewhere? It becomes, how common are the conditions for life? Because if 2 nearby worlds around a small red star can hold the right ingredients, then the galaxy may be far more alive with possibility than we ever dared to believe.